Can you see the screen with the presentation?
Yes, we can.
Yes.
Okay. So this is the most important slide. This is the title. If the title is clear, the rest can be. This is something that there is a long story behind this work. This, let's say, this paper that I have already commented at least once to Adrian. I don't know whether also I commented this to Genaro about the.
So what about if we start right now and then you can tell us the story?
Okay.
Shall we start?
Yeah.
Yes?
Yes.
Okay, so then welcome to the seminar again, the optimization over nonlinear model spaces. And today I have the pleasure to introduce the speaker. I think that everybody knows him. Also, he has confessed that he's a little bit nervous for the talk. So, Justo, Puerto, this is a pleasure to have you this afternoon. So you can start with your talk.
Thank you, Maria Ángeles. Thank you, Genaro and Russell, for organizing the seminar and well, give me the possibility to present on the third place, on the third talk, this material that is based on an old work that we started with a former PhD student of mine that unfortunately passed away, and it has been not forgotten but left aside for some years, and we have decided to put it in circulation again. This is now a joint paper after some modification and some changes that we made on the original work by Moisés Rodríguez. Is now a joint paper with Martin Labbé from the University Libre de Bruxelles. And this is about the geodesic path and location problem in polyhedral complexes. This is the agenda of the presentation. So it's as usual, I will give an introduction, and I will tell you the motivation, why we studied this problem. And then I will consider two different problems. The first one is a shortest path problem in this framework. And then once we have a representation of shortest path, we can tackle a location problem. And I will present the single facility location problem, but also a multi-facility problem can be considered. I will say that optimization model in geodesic spaces is an appealing topic nowadays in mathematical programming. And length spaces or geodesic spaces pose interesting challenges in metric geometry with non-positive curvature. In our field, in our case, we are interested in some finite dimension version of the problem, in particular in version which is based on a polyhedral complex where each element of the partition is endowed with a different metric. And the idea is to consider a standard problem in operation research, or let's say applied mathematics, like finding shortest path, and other problems that need as a building block the computation of shortest path, in particular the location problem. Our interest in this problem was motivated by two reasons. The first one was by this paper that we published in 2017 in mathematical programming, where we consider a location problem that we call under the effect of refraction, but this is easy to understand, that is a framework where we have two subspaces separated by a hyperplane in finite dimension, and in each side of the hyperplane we have a different metric to measure distances, And then, the idea was to characterize shortest path in this space, and with the characterization of the shortest path, solving a standard location problem there. When we were working on the paper, we realized that this was a very particular case of something that is much more general. Instead of considering simply two subspaces, one can consider a arrangement of hyperplanes in finite dimension. This will induce a partition, a complex of polyhedra, and then the same problem could be considered. But this is something we did not consider in this paper, and we left for a follow-up paper. For those of you that are not familiar with the location problem, a location problem is a very simple model where we are given, let's say that we are in Rn or whatever finite dimension, and we use Euclidean norm. This point, the dot that appear in the figure, are the demand points, and then we want to find a new point that we call the facility that will try to minimize the sum of distances of the sum of weighted distances from the demand point, the AIs, to the point X. A solution could be something like this. This is always star shape. We find the solution, and then we measure distances, segment, shortest path from X star to the AIs, and then we account for the overall sum. In that paper that we consider, there was some two part in the space, and in one part we measure with one node, let's say L2, and the other we can measure with L3, and then we characterize the gate point, so the point where we have to change the media from one side to the other. This was, it was not by chance that we consider this problem, because there has been a long list of authors considering this problem in the literature, where they solve particular instances using particular approaches, geometric argument, and characterizing this gate point and some other things over the years. And then we enter in 2017 giving a formal description where all those cases were addressed under our framework. Surprisingly enough, 1 year later, it appeared another paper that also solved a particular case that was also covered in our paper, but more surprising was that was published by people in our own university from Sevilla. Concerning this problem, there is a very nice relation with the physics law that is called Snell law, that governs the trajectory of light rays when they traverse different media with different refraction indices. The light always tries to move using shortest distance, shortest path, and then when we have different refraction indices, appear the effect of refraction. That is what we can see in the figures. And this is something that we also analyzed in our previous paper, and gave a general view, or let's say a more general view of the Snell law that was already known in physics. The second reason that we had to consider this problem was the relation with a very well-known problem in operation research that is called the weighted region problem. The weighted region problem was a problem introduced by Mitchell and Papadimitriou in 1991, and it consists on solving a shortest path problem in a polyhedral complex in R2, where every element, every polyhedra is endowed with the Euclidean norm, but with different weights. It's no, this is a location problem, no. This is, for instance, this is an instance of a weighted region problem where we have this polyhedral complex, and in each cell there is a different weight so that when we try to find the shortest path between the point that appear in the cell, do you see my mouse? No. Well,
yes, we see.
Yes, we see the mouse.
So here the idea is to find the shortest path from this point. This is the initial point until the end point, which is in this other cell. And as you can see, depending on the weight that you put on even using Euclidean distance, weighted Euclidean distance, you see that the shortest path curves somehow, and it tries to find those cells where it's cheaper to move because the weight is smaller. No, this goes in the other way. What was done by Mitchell and Papadimitriou was an extension of the so-called Dijkstraat algorithm that is very well known for shortest path on graph, and they extended this algorithm to the continuous for introducing a Steiner point based on the optimality condition, that local optimality condition of the path when it traverses from one polyhedron to the adjacent one. And of course, this is somehow a connection with the Snell law of refraction in physics, and they study some special structure of path. The problem that eventually we want to address is a problem like this, where we have this polyhedral complex, we have a set of demand points, these are the black dots, which are spread in the space, and in each cell there is a different norm, in this case of the family LP, ranging from L1 to L infinity. And in the end, we want to solve the problem. We want to find the point minimizing the distances. It's like it's not a centroid because we are not using a square Euclidean norm or P power LP norm. We are simply using the norms, but it's like finding a median point for the location. And in the end, we want to solve this type of problem, not in R2, but in any finite dimension space. This is the example of the weighted region. This is a weighted region shortest path. Let me put into the framework that most of the approaches to solving this weighted region problem has been done using approximate solution. In most of the paper, what they do is that they approximate the solution, but none of them consider finding an exact solution for the problem. Okay, because everything is based on finding some Steiner point, approximated Steiner point that approximate the gate point between adjacent regions. There is a reason that has been discovered recently for not solving exactly this problem. In 2014, it was proved that the weighted region problem cannot be exactly, this is important, the exact solution cannot be computed on the rational using, let's say, arithmetic operation. And this is why, so far, it is not known, as far as I know, the complexity of the problem is not known if it is polynomial or is NP-hard, and most people think that the problem probably cannot be solved in polynomial time. What we want to do is something different. We want to use a different approach. We want to embed this problem into a mathematical programming formulation. So we will put an objective function and constraint, some variable and constraint. And in the end, we want to have a mathematical programming formulation that can be put in a solver, so that with off-the-shelf software, we can solve instances of the problem up to a given size. Of course, this type of problem will need the use of binary variable, because we have to make decision. And most of the time when we use binary variable, the result is worst case exponential, because in some cases we have to do branching and we have to search over the tree of possible values for the binary variable. But okay, this is in principle. Okay, so this is the motivation, this is the framework. Now, as I mentioned before, I want to consider two problems. I want to consider the shortest path in this framework, and then I will also extend the problem to the location problem. Now, what we do is the following. Remember, we have a polyhedral complex. No, I don't know. No, it's not here. We have a polyhedral complex that is induced by whatever you can think of, an arrangement of hyperplane or whatever. You have convex polyhedra which are connected, and then we associated with this complex a graph where every node of the graph corresponds to one of the polyhedra, and the arcs are given by interfaces between adjacent polyhedra. Okay, so we have the complex, and the complex is transferred to a graph where the vertices are the polyhedra, and the links, the edges, the arcs are defined by interfaces between adjacent polyhedra. We will represent by x of pi. Adrian has a question, maybe. Adrian? I cannot hear you, Adrian. No? No question? You appear mute. No, Adrian, I can't hear you. I see you well, but I see that you are moving your mouth. Yeah, but sorry, I don't know whether Genaro can give you right to.
No, Justo, neither do I. I think it's a problem with Adrian's computer.
Okay, Adrian, I will answer later, if you don't mind.
Yes, I think there is some problem with the Adrian computer. No, let's see later, maybe.
Okay, right. Okay, so I will continue, and then we have a string. We have defined. Let's say that the input of the problem are the extreme point of the polyhedra that are defined in the complex, so that we can refer to the extreme point of polyhedra pi as this x. And for the interfaces, for faces of different dimensions, we have a phase between two polyhedra, and then this is just simplified to consider problem in R2, okay? So to simplify the presentation, everything is referred to R2, so that we have phases of full dimension, which are dimension 1, and then we have interfaces between polyhedron I and J, and the stream point that define this phase. Every polyhedron is endowed with a different norm of the family LP, so LPI will be the norm that is associated with the polyhedron PI. And we have a starting point XS that belong to this PS, and a terminal point XT that belong to PT, and these are the starting and terminal point for the shortest path. Now, then to solve this problem, we consider the set gamma of all the simple paths. Well, I must say that between the different possibilities for this problem, we are going to consider a simple path, so that we consider path that only visit each polyhedron at most one. This is a simplification, and later I will tell you how to extend to any finite number of visits. Okay, but for the presentation, to start with, we consider that every polyhedron can be visited one. This introduces some difficulties that I will tell you later. In particular, the distance that I'm going to define is not a distance, because actually it does not satisfy the triangular inequality. But it's a measure that is adequate for our setting. So we consider this gamma the set of all simple paths with a finite number of segments, and this sequence S I1 to IKT, it's a sequence of indices of adjacent polyhedra, so that we move from one polyhedra to another which is adjacent. I anticipate that although we are considered general LP node, our scheme only can tackle LP node with rational P. Because if P is not rational, then we don't have an efficient way to represent the norm within the mathematical programming, that formulation that we use. Okay, in general, we can consider LP node with real P, but to solve the problem, we require P to be rational. Then the problem, finding the shortest path, can be stated in the following, let's say, formal writing. We want to consider the distance from XS to XT, and this is the infimum over all the finite consecutive pieces, segment, starting in S and ending in T. And then what we do is that we consider the distance, we measure the distance within each polyhedron using its own norm. If it is weighted, we multiply by the corresponding weight, and then we put all those sequences, finite sequences, and we take the infimum between all of them. Okay, this is the setting. If we assume that we consider simple path, meaning that each cell can be visited at most one, D is not a metric. And there are, I can show you simple example with 3 polyhedra that make the distance, making fail the triangle inequality. Now, if we allow the path to visit a polyhedron more than one, then the distance satisfies triangle inequality, and in this case, the setting corresponds to a complete metric space, and in the complex, the polyhedral complex, the space is a length space, so that it has all the properties that are known for length spaces. In particular, if all the nodes that are used in the polyhedra are strictly between 1 and infinity, then these are geodesic path, and these are also uniques. But I tell you that I will work in the other setting. We will work in the setting where paths are simple. Now, everything here is based on local optimality condition. Local in the sense that we need to characterize how is the gate point that we need to find to move from one media, let's say from one polyhedron to the adjacent polyhedron. And this is governed by the Snell law in physics, that essentially tells that we want to find a shortest path. So if X is the point in the separating media in the hyperplane, we are trying to find X on the hyperplane, minimizing this problem, which is a nice convex problem, okay? And this is a problem that in finite dimension always has an optimal solution, so we can forget about the infimum, and we can find exactly the X. Actually, the characterization of the optimal solution is given by this relation between sinus of angles. These are the angles that appear in the figure, and the point X that satisfies this relation is the optimal solution for the problem above. Of course, this is based on using Euclidean distance, because everything related to the geometry of the Euclidean ball. And this is the standard trigonometry. When you move and you use different distance, not Euclidean distance anymore, this is not true. And then you have you have to solve the problem using norm P, norm Q, whatever, and then the solution is different. It happens something that one one can characterize that this is something we did in our previous paper, using that we call the P sinus of, and again, one can characterize the problem, the solution X star. In this setting, in new setting, we have given a more sophisticated condition that given 2 points A and C in two consecutive cells, let's say two adjacent polyhedra, B will be the gate point if it satisfies the condition that appear down here. And this is a condition that involves, this expression that comes from solving the Lagrangian problem that I showed before with the corresponding piece. This form does not show something similar to the Snell law because there are no sinus, no cosinus. The sine is the sine function, which is 1 minus 1, depending whether it's positive or negative. But there are no angles here. Actually, one can find something that relates this condition with the standard Snell law using a relation between the polarity of the norm used in the two polyhedra, and we extend the notion of polar vector that allows to define, let's say, P angles. And based on those concepts that I'm not going to elaborate today, this is formed in a scalar product form, and then from this scalar product form, one can move to this alternative form, which is in cosinus form, that tell you when a point B is the gate between A and C. But the interesting thing, again, I'm not going to give detail, is that here, this phi of Pi is the angle that we are considering between this vector, and this is not the standard angle, but what we call the Pi polar angle between this vector and this vector. It's a bit technical, but in the end, it shows that there is also some form of relation based on trigonometry, but let's say not a standard angle. In other words, one can characterize local optimality in this problem using something similar to the physics Snell law that is valid for L2.
Justo, could I ask a question?
Yes.
So sorry, I finally got my microphone working. So I actually had two questions. So one of them was about the polynomial time thing that you put up earlier. So is that are you allowing dimension to vary there too? In that sort of belief that people have that it's not polynomial time, is that they don't even believe it in 2 dimensions, or?
The dimension is part of the input.
I see. Got it. Okay.
Dimension
So
is part of the input. So
the other question I had. Maybe you can give me some intuition here. So I was curious about the uniqueness of the geodesics result. It just seems to me if you have a region in the middle of your region that has a very high weight, then you could imagine like a geodesic path going either to one side of it or to the other. It's sort of, I'm sort of curious as to how the geodesic can be unique. Do you see what I'm saying?
You mean because you will enter several times to the same region?
No, I mean if you imagine that you have a planar region, yes, split up in a grid, let's say, and one of the squares in the grid has a very high weight.
Yes.
Then you could imagine your paths might want to go either above or below it, and they might both be the same length, right? Because they want to avoid that region.
Yeah.
I'm wondering where is my intuition wrong here?
No, it's not. Well, You mean that there might be symmetric?
Exactly.
It might be true.
Right.
It might be true that you may have symmetric. I have to check this because the idea, because this is not. It was just based on the fact that if you have a strict norm in the grid, there is always the shortest path between. There must be always unique, but it's true because this is like a forbidden region, and to avoid the forbidden region, you may have a symmetric. It might be true. I have to check.
But we can come. Yeah.
Yes.
Very good.
I'll check.
Thanks.
Okay. Okay, so we were here. These are the actually we are not working in that framework because we want the path to be simple, and in this case we don't have uniqueness because we may have also different things. Now we can exploit this optimality condition, developing something similar to the Dijkstra algorithm that was the continuous Dijkstra algorithm, which is based on some recursion dynamic programming, so that we work backward. We start in the end point and we're trying to find which is the gate point in the adjacent region, and this is computed with the d, with the function d that measure the distance that we want. And when we have this defined, we can use this recursively to compute distances to other points using the optimality condition. So that when we have this functional that measures the minimum distance from a point that is in a particular pk, which is not the final one, until the final one, then we can decompose the problem in finding the first segment that goes from the point to the next adjacent polyhedra, and then from this point we compute the optimal minimum distance from the next point to the end. So this is standard thing. This is like dynamic programming, but the only thing is that to solve this problem, we have to check that the point that we use in between, this ti minus ti plus 1, satisfy the optimality condition. And the optimality condition, as you remember, it's something that must solve a convex problem over a, let's say, a convex phase. And this is a problem for which we don't have a closed form formula. So we don't have an expression, a closest form expression for this functional f. So although we can solve this, theoretically speaking, we can evaluate f because we can solve for every ti, we can solve the problem. We cannot evaluate all the points in a continuous form. So this is valid in some sense, but it's not tractable. But what is interesting is that although it is not tractable to solve the problem by itself, it gives us the intuition to solve the problem with our formulation. Okay, this is what I said. Then the approach is based on the following. We want to define variable Zij that will be a binary variable that will assume the value 1 if the arcs ij is selected in a simple path from S to T, and will be 0 if this arc is not used. It means that if our shortest path goes from polyhedron I to polyhedron J, then we will activate the variable Zij. Otherwise, this variable will be 0. And then we will use also a continuous variable Yij that will represent, let's say, coordinate of the gate point in the interface between polyhedron I and polyhedron J. So this will be the element that we use in our formulation. The formulation, formally speaking, is this one. The objective function, we try to minimize something which is the length of the path that we consider. So this term represents the first segment from the starting point to the point that we choose in one of the adjacent polyhedron. And this variable activates the addend or not. If this Sij is 1, it means that we will move from polyhedron PS, the original, the starting one, to Pj. Otherwise, it will be 0 and the term will not appear. Then this term in the second place will handle the segment that move between consecutive adjacent polyhedron, which are not the final one. And this is why we use two binary variables, set hi, set ij, that when both are equal to 1, mean that we will move from polyhedron H to polyhedron I, and then from polyhedron I to polyhedron J. Otherwise, the term will be 0, and it will not be accounted for in the sum. And the last one is the same, but only for considering the last segment in the formulation. So assuming that the set variable and the y's, which represent the gate point, are well defined, this objective function will account for the length in our setting. Now, the three first conditions are flow conservation constraint, and essentially tells here, this is tell that only one segment will go out from starting point X. Okay, this is flow conservation, and it tells that between two consecutive polyhedra, we will enter one and we will get out in the other, so the balance will be 0. And the last one tells that there is only one arc, one segment entering in the last polyhedron. So these are somehow, we call them a standard flow conservation constraint to ensure connectivity of the path along the complex. And these two constraints, what do is that they ensure that the path will be simple, because only one arc can enter in polyhedron I, and only one segment can go out of polyhedron I. So in the end, at the end, we are ensuring that the path is simple. The thing that it suggests to define is that we need to represent the point y, which is a point that is in the interface between S, let's say between I and J. But this is something we can do using the extreme point that we will see in the next slide. We will use extreme point of the interface, and then we use another the variable will be the convex, the variable in the convex combination that represent this point. Here you can see what I mentioned before. Lambda, the y's are the sum here. These are the y's, because are the convex combination of the stream point of the interface, and the lambdas are the coefficient in the convex combination. So what we have done is that before we have this term that were norm, and now we replace those terms by this auxiliary variable d, which is greater than or equal to the term that appear in the objective function. And since we are minimizing with non-negative weight, in the end, d will be equal to the distance. And if this is well represented, in the end, we are computing exactly the distance that we wanted to do. This constraint, which is also new, tells that we need to use coefficient in the convex combination only if we use the interface. Otherwise, this is 0, and then we will not use the coefficient in the convex combination for the interplay, for the gate point in the interface ij. Okay, this is a formulation for those which are familiar with mathematical programming. We don't like this type of constraint, because what we like is to have essentially linear constraint, if not something which is, let's say, maximum second order. And okay, but this is what we have. Now, one can also modify this constraint, this thing, defining new auxiliary variable that account for the multiplication of variable in the previous formulation. So if we introduce these variables, rho, phi, and c, which are multiplication of binary variables, so binary, this is multiplication of a binary times a continuous, so it's semi-continuous, still linear, we can linearize, and this can also be linearized. We can have another formulation. I have to say that this is not a simple lifting because we are involving conic term. And the lifting usually is used when you have the standard lifting is used when you multiply thin variable and to remove in linear constraint. So this is somehow something, it's some type of lifting, but more sophisticated. Now, after some algebra, one can prove that the norm that in the previous formulation was outside, we have the norm of the sum, one can substitute it by something which is stronger and still valid. So we can have this, paying the price to multiply the variable times the set. And here again, we can do the same. We can have this before norm were outside, but now we can put inside. And this give us something which is stronger. So enforce better the constraint. And also this is a valid variable, but we have to linearize this new variable, this auxiliary variable, which are multiplication of previous variable. So we need to linearize, and this is done with this constraint. Okay, this still we have this, which are p norm. So we have constraints that involve p norms, which are somehow not nice, but these are well known to be second order cone representable, and you can use the one result that there are some other results, but this is one which is particularly attractive because it's almost optimal in terms of the number of constraints that one has to use to represent things, so that in the end one can have this constraint, which is a p norm p constraint, and this can be written equivalently by a set of logarithmic number of rotated second order cone constraint. And in the end, we can transform the problem into, let's say, a friendly problem. Well, these were the two formulations, and then we asked ourselves the question whether it was stronger, and we could prove that the continuous relaxation of the second one was stronger, meaning that when we start solving the problem, we start from a better point. So theoretically speaking, the first formulation gives a weaker continuous relaxation. This is also something that one can expect because it has a smaller number of variables. In the second formulation, we have more variables, and then essentially what we are doing is that we are having a better representation of the domain. Well, this is a picture that I will use to tell something about the pre-processing. In this type of formulation, there are many variables. You see, there are many variables. There are many sets because there are per each pair of adjacent polyhedra, we have a binary variable and we have a representation of the y. So everything scale bad, let's say. If we increase the number of polyhedra, the formulation increase quadratically speaking the number of binary variables. Then to try to avoid this question, we develop a pre-processing phase to fix to zero some of the set variable. Remember that the set variable tells whether the optimal path will pass through two adjacent polyhedra. And then what we have observed is that you want to consider the shortest path from the, let's say, from this corner to that corner. Of course, in general, it's not true, but in most cases, those polyhedra which are along the boundary are not used. And this is something that one can check exactly. It's not heuristically. One can check whether the path goes through or not. Because the point is we only have to force one variable to be one, and then it means that we'll go from this to this. So if this set ij is one, we will force the path to pass through this interface. We are not going to solve the problem, but we solve the continuous relaxation, which solve very quickly. The continuous relaxation gives us a lower bound. And this we can compare with the feasible solution. And the feasible solution that we use to compare is the standard. We trace a straight line between the origin and the destination, and we compute the shortest path that goes through the region defined by this straight line. This is something we can compute because this is a geometric construction, and this gives us an upper bound. We know that the shortest path will give a value below this. Now we compare this upper bound with the lower bound obtained by the continuous relaxation fixing this variable to 1. And if this is already above the shortest, if the lower bound is above the feasible solution, we can discard these two regions. And this is something we have done for a number of regions. Essentially, one can try all, but these are many. So we try 10% of the most remote region or 20%, and then it allows us to fix a lot of binary variable to zero, which simplifies the problem a lot. This is what is explained in this algorithm. And now I will tell you something about the setting. We have randomly generated instances with n polyhedra in the 010 square in R2, and we associate to each polyhedron one of the norm in this list. The starting and terminal point are set to the lowest left corner, 0, 0, and the endpoint to the upper right corner, 10, 10. We generate 5 instances for each value of m. M is the number of region, and we set a time limit of 2 hours. And well, we solve those problems, reporting the average running time and the average gap in case that the problem is not solved to optimality. Everything was coded by Moises in Express with the version 8.9 and using for the setting for the polyhedra, we use MATLAB in a computer with this characteristic. Okay. These are some results. Well, if we consider a setting with 50 polyhedra, using the first formulation, you can see that we solve essentially all the instances because the maximum gap was 0.01%. So it means that all were solved to optimality. With 100 region, we solve, we start to have problem because there was some instance that had a gap of 6%. And the minimum was 184. It means that none of the instances were solved to optimality. We were close to probably we had the optimal solution, but we were not able to close the gap. And when 150 instances in 2 hours, gap were already some non-negligible because the minimum was almost 8%. So it means that the first formulation worked well until between 150 regions. If we move to the second formulation, the one that has more variable and also was stronger, one can see that essentially we solve all the problem up to 300 regions, which is some advance. But also 350 region, the maximum gap was 0.5%. It means that probably these are rounding errors. Also, for 400 region, we have already 4% gap. And we solved some instances, but some other were not solved. This was pure formulation without preprocessing, without the strengthening. If we use the strategy that I mentioned before, trying to fix to zero some variable that will not be used in the optimal solution, then the situation improves. And for the second formulation, preprocessing only 10% of the region, so those which were farther away from the, let's say, the straight line path, we get solution like this. It means that you can see for 450 region, the maximum gap was 0.9%. So it means that essentially we solve all instances. And for 500 region, we have a gap of 2.5%, which is acceptable. So the problem using this implementation, that probably is not the best one, can be handled up to a number of regions which is reasonable. So 500 region, it's we were very happy. Well, this was for the first problem. I mentioned that the problem can be extended to consider not simple path. We can consider any number of any finite number of visits, because the only thing one can do is to replicate in the graph. We replicate the polyhedra. We make copies of P1 like Pn plus 1, and then we will allow simple path in this extended graph. But if it's the path visit P1 at Pn minus 1, it means that it has visited the original polyhedron P1 twice. And this can be done for any number of finite number of visits. The only thing is that we enlarge the graph. The graph will be larger. We are multiplying the graph time the number of visits that we allow. But we know that the maximum number of visits that will occur in this setting, this is something that was proved before. It's of the order of m. So if we make m copies of the original region, we will solve the problem. Let's say the problem in a metric setting. Okay, now the second problem, the single facility, the location problem with different norm. Well, the idea is to exploit what we have developed for the shortest path, because essentially we need, no figure. Essentially, what we have to do is that we have to compute shortest path from every demand point to the new facility. So if we have demand point L, we need to introduce a set of variables, let's say indexes L, meaning that it will represent the path starting from the shortest, from the demand point L until the new facility. So replicating this set variable and the y variable for each demand point from 1 to n, if we have n demand point, and introducing a new facility, a new variable ui that will tell us whether the new facility is in polyhedron I or not, we can have a representation of the problem using very similar constraint as before. And this will be the formulation type number 1 based on the representation of path using the path formulation F1. And this will be formulation type F2 using representation of path based on the rationale of the second formulation. The only thing is that we have replicated n time the variable that correspond to the different demand points. Many constraints, many things. Again, we can prove that the second formulation is stronger because it gives a stronger lower bound. And now there is also another pre-processing strengthening that we can use. But now we can use the first one, but we can also use the one that valid for path can be used, but there is another strengthening based on fixing the polyhedron where the new facility is going to be placed. In this case, the optimal solution is here. So we have introduced variable UI telling whether the new facility will be in this or that or that or that. So there are many. If we have a large number of regions, we have used variable one per each of these regions. So we have, let's say, a large number. But with this configuration of point, one can think that it's very unlikely that the new facility is going to be located in the, let's say, outer regions, because the point, it should be located somehow, let's say, well placed with respect to all the existing facilities. Now, we have developed a test that also computed lower bound for the solution, forcing the new facility to be placed, let's say, in this region. We fix this U equal to 1. We solve the continuous relaxation of the problem, which is a continuous convex problem, second order problem, which solve very quickly. And then this gives us a lower bound. Then we compare this solution, this value with the, let's say, a standard solution computing distances using L2 norm for the location problem. This will be an upper bound for the optimal solution. Now, if the solution placing the new facility here, the linear relaxation is greater than this feasible solution, we can discard and we can fix to 0 all the variables that are around. So we have two strategies to fix variable, one to fix set variable, another one to fix U variable, and this help in solving the problem. Again, we have a setting similar to the first one for the shortest path. And we use, for doing this set, we use data set that are benchmarked from the literature. Particular, we use a set of 50 demand points from Elon Watson that appear in a book by Elon Watson, Christophe. It's called Distribution Management, and also the set of points by Parlar that appear in a paper in '94, and another set of points that appear in this paper by some set of Iranian authors. Again, we use the same setting, the same type of norm, and we report CPU average time and gap at termination. The results are, I'll show you only a couple of tables because the time is running very quickly. These are results for the first formulation with this number of regions, between 5 and 20, with 50-point data set. This is the data set from Elon Watson. These were with norm, unweighted norm, and these were with weighted norm. So as you can see, for 5 regions, the problem solved to optimality in all cases. And then for 20 regions, you can see that none of the instances was solved because there was already, the minimum gap was 12%. When we use weighted region, the behavior is similar. We can solve up to 15 to optimality, and then for 20, let's say the solver struggles. Now, the second formulation performed better, as you can see. For no, that not perform better, perform equally. So we have similar result. We can solve up to 10 to optimality, but then to 20, there is a 4% gap. And then in the weighted case, we also have some gap. In the end, we have many more table, computational result for different settings, but the behavior is somehow similar to this. The conclusion are the following. We have derived mixed integer second order comp programming formulation for the problem using general LP norm when P is rational. Using the representation of LP norm as second order comp program, there are several ways, but we use one that we developed in 2014. We have proved that one of the relaxation is stronger than the other because it provided better lower bound, even though it has a larger number of variables that sometimes make the problem to get slower when the sizes are larger. We have developed pre-processing algorithms to tighten the lower bound, fixing variable using very intuitive ideas of what should happen with the shortest path. And we have solved instances up to 400 regions for the shortest path problem. And some classical instances in the location problem that were previously only solved for very particular cases with 2 regions. Another thing that we think that is very interesting is that as a byproduct of the result, we have relayed the local optimality condition in this type of problem with an extension of the Snell law in physics through the concept of polarity between the norms that appear. And it gives also something nice, an extension of Snell based on some P angles, which are nice. And that's all from my side. Thank you.
Thank you very much, Justo. Now it's time for questions or comments. If any one of you would like to ask something to Justo.
Maybe I have a question, Justo, again. Okay. Is my microphone still working?
Yes, we can listen to you.
Justo, could you put up the location problem that you solved again, the picture?
The picture, you mean?
Yeah. I just had a dumb question about that.
This?
Yeah, that one, yeah. I'm confused about what's happening in the bottom right-hand corner, because it seems like you have 2 geodesics that are crossing there. Which shouldn't be the case, right?
No, but these are not geodesic in the sense that these are. It might be that this is not the optimal solution, and this is just a representation of a solution that. But in the end,
I mean, maybe that's just an approximate solution returned by the second order cone relaxation somehow.
Yes.
So it's not,
might be the solution which is not solved to optimality.
Right.
But what you say is that it would be better to move from.
Yeah, it can't be the case that you have geodesic crossing, right?
Yeah, but remember that these are not geodesic because this is not a metric.
Yeah, I understand, but the paths somehow that you're joining somehow, it seems. Yeah, I guess it seems like you could do better than that, right? If you've got those 2 paths crossing, then you should be able to do better, it would seem.
Mm-hmm.
Anyway, so that was one question. The other question I had was, so there's this notion that these problems are hard, and I'm wondering, so the some of the questions that Genaro and Adriana and I work on are very special cases of these, where, for example, you might take a square complex in the plane, where all the regions, the distance is just Euclidean distance, but some of the squares are missing. Like so you have some missing squares, and in that case, the geodesics are polynomial time computable, as long as you end up with something simply connected, right? So as long as you don't have holes, for example. So you can imagine that there are special cases where it's much quicker to solve. And I wonder if you've thought about, you know, those special cases where it works faster somehow.
No, we did not consider this. Actually, the problem that we are considering is a problem where the simple path that we consider, the simple path are defined by segment, where you use between 2 points within element is the arc that you use is a straight line. So the solution that you mentioned, where you will move in the, let's say here, from this, and if this is the shortest path, this path will turn moving, sorry. So this part will move to here and then will jump to this. This is something we do not allow in the path. In the set of paths that we consider, the gamma set that we consider at the beginning is defined by a finite pieces, so that within a polyhedron, you use a straight line. You don't have piecewise linear path. This is the definition that we use. This is what is defined in gamma.
More questions, or Adrian? No. Anyone else?
Actually, the local, this is something, this is interesting, this poses interesting question, because depending on the point that you move from the gate to, it will be better to go to something different. The gate depend not only depend on the point you enter and the point you go. This is what tells the optimality condition. So from this point, you may go to this, and then it's better to move to this. And from this, you will go this because you will move to this. And depending on the position of these two, the gate will be different.
More questions or more answers? If not, thank you. I think that we are gonna close the session. Thank you very much, Justo, for such an interesting talk. And I think that the next seminar will be in 2 weeks, Genaro? Genaro, your microphone is off.
Okay. Sorry. Yes, is the next seminar is the 28th of May. Okay, and it's going to speak Ariel about basically subgradient methods in cut zero spaces. I think you can find information in the web page of the ONMoS, but in any case, we will send in short the announcement. Just to remember the people, now we are going to start to program the seminar for the fall. So if anyone is interested, okay, let me know, or either you want someone that could be interested, okay, in order to, our idea is before the end of June have the program for the fall, okay? If any question, any case, hey, Adrian and Adriana, could you stay for a minute? I want to comment something with you.
Oh, no, really?
More questions. Okay, so if not, thank you to all of you to participate in the seminar, and in Sundays we will send the announcement for the next talk. Thank you very much, and see you soon.